Okay, this is going to be the last of the lessons on the historical development of quantum mechanics. So today we're going to talk about the de Broglie wavelength, de Broglie waves. This thing right here is pronounced de Broglie. In my earlier videos, I may have pronounced it as de Broglie or de Broglie, but apparently the correct pronunciation for that is de Broglie, de Broglie. Okay, so we're going to talk about de Broglie waves and the uncertainty principle in this lesson. Okay. So de Broglie's hypothesis was this. He made this in 1924. He said that if light has particle-like behavior, then maybe particle also behave like waves. Okay. So if you recall, we said that for light with wavelength lambda, the momentum is equal to h over lambda. So p is the momentum. Or you can say that the wavelength is h divided by the momentum of the photons that make up the light. Okay. Now, de Broglie suggested then that for electrons, for matter, for particles, electrons would also have a wave associated with it. So for what we would call matter waves, the momentum, since the momentum is mass times the speed, de Broglie suggests that, well, maybe wavelength is going to be equal to h over the momentum, and momentum is mv, so the wavelength associated with a particle of mass m moving at speed v would be h over mv. Now, if you're dealing with very high speed particles approaching the speed of light, then you're going to have to use the relativistic mass. You're going to have to replace the mass by m naught here over the square root of 1 minus v squared over c squared. So you have to do the relativistic correction. M naught is the rest mass. Okay? So, consequences of wave-like behavior would be things like diffraction, just like light. Okay? And this is a very nice, very great video. I think this is the best one I've ever seen about wave-particle duality and introduction to quantum mechanics that I've seen from Yale, and this one's from Yale. So I'd like for you to look at that first. Okay, this one talks about the wave-like behavior of electrons, and so it also talks about the consequences of the wave-like behavior, which is the uncertainty principle. Okay. One thing before you watch this video is that to know is he uses the symbol h bar, which we'll be using later on, and h bar is simply defined as h over 2 pi. Okay, so let's take a look at that. Also, there's another website. This Colorado Physics 2000 website has a nice animation of diffraction of electrons. Okay, so that's something you probably want to take a look as well. So let me pull up that website for you. Basically what you do is, okay, I already have it here. If you were to do a search on YouTube, just search for Yale Quantum Mechanics. Oops. Oh, sorry. Yale Quantum Mechanics. And it will take you to this lecture number 19 for a physics class at Yale. Right? And this is the video. And if you click on show more down here, you can see at the 36-minute mark, that's when it starts talking about the wave-particle duality of matter. And one of the consequences of that wave-particle dual nature of matter and the wave-particle duality for light is the uncertainty principle. It talks about that starting at the 48-minute mark. Okay, so now this is a very good lecture, chalkboard lecture. If you want to start from the very beginning, he gives you a review of the wave nature of light, okay, the double slit experiment that showed that light is a wave, and then at the 9-minute mark, it starts talking about the particulate nature of light. We talked about that earlier in this class, and the experiments that demonstrated that light behaved like particles, the photoelectric effect. Compton scattering is an experiment, a phenomenon that demonstrates photon momentum. Okay, so if you have X-rays, an X-ray hitting an electron, an X-ray photon hitting an electron, you see the wavelength of the X-ray changes. The shift in the wavelength is due to a change in the momentum of the photon. All right, so let me go ahead and play this for you. I need to stop recording because I'm going to be putting this up on YouTube, so we'll pick up the recording of this lecture once we're done with this part of the lecture. Okay, so I'm going to let you watch from the 36-minute mark, wave-particle duality, on towards the end up to where it starts to talk about how wave-particle duality leads to the uncertainty principle. Okay, so let me pause this recording.